Now, let's do one more example, okay? So, how about we have a declining population of deer in a certain forest. It shrinks by a factor of 4/5 every 2 years, okay? So, a factor of 4/5 every 2 years, okay? And it starts at 1600, okay? So don't let this fool you. It's still going to be as simple as the last one, okay? Even though 1600 is a big number, okay? So we're going to define a variable, obviously. So let's say y is equal to years, okay? And we can set up a little function, okay? So y and f of y, okay? So we know that it starts, so when it's at 0 years, it's going to be 1600, obviously, because it starts at 1600. Okay, well, I actually might get out my calculator for this one, just in case. So now let's say, okay, well, let's say 2 years have gone by. Well, after 2 years, we're going to multiply 1600 by 0.8, and that gives us 1280, okay? And we can do it one more time at 4 years. At 4 years, we multiply again by 4/5, or 0.8, and we're left with 1024, okay? So, after we did a little test, let's start writing it down. So we know our base is 1600, and we're multiplying it by what? Our factor, which is 4/5, right? And we know that when we know that when y is equal to 2, the exponent is equal to 1, right? So when y is equal to 2, the exponent is equal to 1, because we're only multiplying 1600 by 4/5 once, right? And then when we go to 4 years, right, when y is equal to 4, we're multiplying it by 4/5 twice. So when it's at when y equals 4, it's going to be 4/5 to the power of 2, right? So how can we write that? Well, we got my eraser, and we can write that as y divided by 2, okay, right? So 1600 times 4/5 to the power of y divided by 2, right? And we can even test this out. So let's do 1600, and let's say after 2 years, okay, 1600 times 4/5 to the power of what? Y is equal to 2, so it's 2 divided by 2, which is equal to 1. So it's just 1600 times 4/5, and that's 1280. Okay, so look at that. So this is our equation right here for the declining deer population. Okay, I just want to get something out of the way. Those examples are completely made up. I don't know anything about bacteria population or deer population or any of these other examples. I'm just making these up for the sake of exponential models, okay? So just don't go after me for this. So, finally, we'll do some more advanced interpretations of exponential models. So, let's do one example here. How about we have just 2.25 to the power of t/2 plus 5, okay? So, let's try to figure this out. How can we make this simpler, I guess? Well, how I look at this is, okay, well, we know our exponential property. When you see two exponents being added, we know that we multiplied the bases, right? Or at least two powers with the same bases, okay? So, we can break this up into 2.25 to the power of t divided by 2 times 2.25 to the power of 5, okay? And I'm just going to get out my calculator real quick. 2.25 to the power of 5 is equal to 57.67, about, okay? We'll just round it there, okay? times what? Well, knowing our other exponential properties, we know that when you have an exponent to the power of an exponent, you multiply them, right? So we can rewrite this as 2.25 to the power of 1/2 to the power of t. And we know that when you have something to the power of 1/2, it's just finding the square root of it. So the square root of 2.25 is 1.5. So we can rewrite this as 57.67 about times 1.5 to the power of t. And with this, we can definitively decide that this is growing, right, because it's a 1.15, growing by a factor of 1.5 every unit of t, which I don't know, that could be days or years. I'm too lazy to make an example for this one. Now let's work on having to interpret exponential models where we're switching between units of time, okay? Now let's say that this model right here, how about 120 times 4 to the power of t, represents a newly introduced bunny population and its growth every decade. Okay, so t equals decades. Okay, so by what factor does this bunny population increase every year? Okay, well, how can we figure this out? Well, we know that a decade is equal to 10 years, right? So we can rewrite this as 120 times 4 to the power of t divided by 10, right? So well, we want to figure out how much it increases every year. So using our exponent properties, 4 to the power of 1/10 to the power of t, so that's the 10th root of 4, okay, which is going to be smaller. Let's see. So we know every year the bunny population grows by a factor of about 1.15. And this is our new equation for the growth of the bunny population every year. Hey guys, so thanks for watching. So today we covered exponential models and different kinds of ways to interpret them and how to construct them on your own. I strongly suggest checking out Khan Academy because even though stuff like this is simple, I think that you need a lot of practice and to see the different types of models and problems out there. Thanks for watching. See you in the next video where we'll be talking about logarithms, one of my favorites, and peace.